Hello, everybody. Welcome to my talk on scriptable render pipelines. My name is Jean-François. Most people call me Jeff or JF. I'm field engineer, graphic expert. I've been working for about 9-10 years in the game industry as a graphic programmer. And I recently joined Unity to work as a field engineer. Today, we will briefly talk about the current Unity render pipeline, which we often refer to as a legacy. We will then go on what the scriptable render pipeline is, what's the vision, the goals, and how we built the new foundations, and how to create the pipelines in Unity. I will show a code example of a very simple rendering pipeline, which simply renders a constant lighting. In other words, the basic rendering. And I'll show other case examples for some other algorithms. If I have time, I will show them inside Unity. So the current render pipeline, or what we refer often internally as the legacy, in theory, it's a great render pipeline. It supports 2 rendering modes, forward or deferred rendering, with different options to tweak the renderings. The different options are custom shaders. It allows you to change how we process vertices, or how we do the BSDF, the lighting, and the surface. And also work a bit at the primitive level with tessellation or geometry shaders. We also have common buffers. These allows you to insert rendering calls into the rendering pipeline at different stages. They're sort of like callbacks that you insert into Unity's rendering. Examples of this are shadows, pre- and post-camera passes, and post-processing. There's many others. There's also the option with compute shaders. It allows you to process data and potentially generate other data to be fed in the rendering pipeline. A good example of this is procedural meshes, or even generating instancing data. Post-processing effects are another way to change the rendering output. It allows you to make screen effects. Another important point to mention about the legacy pipeline is that we support multitude of platforms, from mobile to console to PC. In practice, Unity is still a black box, even though you can customize it a lot. It still works and abstract a lot of things for you, like the hardware layer. In other words, you don't have to go at low level and write API code. It still works. Sorry, it still works and hard to configure though, but it's difficult to control for a specific use case on some of the platforms. Example of this is some optimization we can do on mobile for frame buffer and for cache, and also compute rendering pipelines that could be possible on consoles and high-end PCs. The flexibility extensibility problem. This is not a problem for most users. More advanced teams that will want to modify more the look of their games. But it is mostly a problem for us, as we're trying to give the biggest quality to all of our users and rendering as fast as possible. And as mentioned before, the rendering is mostly a black box. Documentation is available. There's presentation and source code. But it's still difficult to understand for most without a source code license. So the prominent pictures, these are images I took from the Made with Unity page. They're simply screenshots of games that shows different use case. There are different techniques, and these are examples of the problems that we might have in when we are trying to optimize the rendering. There's also examples of old techniques that used to be from a couple of years ago, such as Forward, that are starting to come back specifically for things like VR. So here's an example of a 3D game, slightly more realistic rendering, and another more stylized graphics with a similar 3D rendering. Here we have a mobile, Ion Mobile, showing stylized graphics. And then we have 2D game with more high-resolution graphics. And we also have UI games. Here's a screenshot from the Adam demo. This is targeting algorithms or techniques that are more targeted to movies than for games. So all these different types of rendering has to go through the same code currently. And a solution for us was to create a scriptable render pipelines. The idea, the goals for this was that we needed to perform better on modern hardware, possibility to optimize specifically for a single platform, and have also the possibility to remove parts of the rendering, anything that you don't need. For example, low-end mobile might not need the Ion algorithms that you would need on console. We kept anything that was we wanted to keep anything that was performance critical in a C++ and internal to the engine. And what is less critical, we would move it to C# and open source it. The main reasons for having the expression of the pipeline in code is mostly that it's targeted to programmers. It is easier for us to change code than it is to change more complex XML or even a visual graph. We wanted this to be less of a black box and easier to customize. We want high-level code and shader compute code to be released on GitHub under an open source license similar to other projects, such as post-processing, the UI, the networking that are already available. We also want the possibility for our user to create multiple rendering pipelines so they can build something that is more suited to their needs. So either build something with a specific target in mind, something that we don't support yet, or a use case, something more specific for 2D games, or something specific to a top-down or even a text adventure game. We also wanted to make less compromises to support platforms of different ranges. And that goes back from the previous point to make the graphics more performant. Another added change is that it's easier to make changes to the rendering without breaking backward compatibility. A good example of this was in 5.3, if I'm not mistaken. Some changes were made on a specular, and I broke the lighting for some of our customer. With a scriptable render pipeline, we could still provide an alternative for those people to keep the same visual as they had. So the new foundation, as mentioned before, the C++ is doing the more critical code, performance critical code. It does the management over sets of objects with different modes of filtering, sorting, and batching. It also performs all the platform abstraction. The user project will have the C# code and the shader code. This is started from the open source version that is available on GitHub. In the C#, we will treat camera, light, and shadow setup, and also the render path structures and the logic all done in C#. And these will then refer to the shader code that will be run on the GPU. So having a single render pipeline for everything had likely a lot of compromises to make it more flexible at the expense of performance. So we can imagine that we will have different types of pipelines, such as these example. Right now, we only have available the HD, the high definition render pipeline, which is optimized for modern PCs and consoles. It is a DirectX 11 baseline with iron graphics and using a lot of compute where possible. We could also think of optimized instructions for mobile GPUs using the frame buffer fetch or other available techniques. Another example of what we could build is something optimized for VR using more forward shading, MSAA, single pass rendering, and some caching for the two eyes. In other words, use the same visibility results for both eyes. Another one is the low-end device, supporting more 2D games, one-pass lighting, and limit the number of lights, maybe even use vertex lighting. All of these doesn't need to be physically separate rendering pipelines because we can still support some of these through options. So I'll briefly talk about the HD render pipeline and what's the vision and the goal for it. Currently, this is what is found on GitHub. It corresponds at this point to one of the latest beta builds. Currently, it's either 2017.1 beta 2 or beta 3. I'm not sure right now. It changed over the weekend. And it will likely update in the future. And that also means that the API, as it evolves, this version gets updated. Oops. So as I mentioned before, it's developed with PC and PS4, Xbox One in mind. And we're looking at optimizations for mobile. So shaders are, the goal of how we designed the shaders was to be less reliant on shader specialization or defines. It relies more on static batching, and the specialization is only where needed after profiling. It's also a more up-to-date state-of-the-art pipeline for more high-end games. And it's released as an experimental at GitHub, and the official release will be later in the year, more towards October or 2017.2. Here's our just a quick list of features that are getting added to the HD render pipeline. So they're looking at having GGX for metal specular parameterization, anisotropic GGS, subsurface scattering, tile lighting, and more physically based camera. And there's many others. So just as an example, is a screenshot I found laying around of the subsurface scattering feature that shows translucency on the rock. This feature could be used for human skin and any other material that have this translucency. So let's look a bit at the code. So just as a note, this was built on 5.6, the release that we have, Final 3. This is an experimental feature, so the API changes with different releases. And in the final API will be released with when the HD render pipeline will be officially released later this year. So how do you create a render pipeline? First, you need an asset to bind on graphics settings. If you go on graphics settings from 5.6, you have this at the top. It's a scriptable render loop setting, which is simply an asset that you bind on the pipeline. All the rendering will be done through the render function. I will show that a bit later. It's a function on a iRender pipeline interface that we provide. So what goes into that render function? All the culling for the cameras. We also call the command buffer to set up global parameters, render targets, and dispatch compute shaders. There's also a series of calls to scriptable render target draw renderers, or other similar functions that will be shown a bit later that process the set of objects. So just as a note before I show a bit more code, this demonstration is not the recommended way to start creating a scriptable render pipeline. I am starting from scratch and showing how you slowly build a very simple scriptable render pipeline. The recommended way is to actually start from the code on GitHub and start modifying as you need. So an example of the flexibility that you have with the version, I forgot to point the builds here. The different builds correspond to your version. And sometimes there's a bit of flexibility because I used a 5.6 beta 10 on the released version, and it was not much difference. So here's an example of the class, the base class, to create the render pipeline. This is a very simple and almost empty class. And in the next slide, we'll show the structure of the render function. Sorry, I forgot. This is the asset. This is also a very simple class. I'll show later more detail in the code. But this is just to show the asset that we bind. At this point, it's empty and doesn't contain any option. Just to show exactly what creates the asset. It's just a simple function. So the render function itself, I removed the code at the bottom with a comment here just to focus on the structure. It is essentially a loop over all the cameras. And we start by doing the calling and then setting up the camera properties and then submitting our work on the context. So here's the rendering code. This was the code that was removed. First, we create a command buffer and start by clearing the render target. Then we can execute this since we don't have any other things to do. And then we release the object. To do an actual draw, what we do is that we create a draw render settings, which we give it the list of results, the current camera, and we tell it which shader pass to use, which corresponds to what you have in your shader. We give it some sorting flags, so it knows which order to sort. And then on the next line, we set the input filter to only have the opaques. And then we call the function draw renderers that executes on all the objects. The last two lines are simply to say that we're drawing the skybox. So it's a simple one function. Just to show, these are the sort flags. So it allows you some control on the order the objects are rendered. This is simply what we have at the... It doesn't seem to work. That's simply what we seem to have here. And we could sort back to front, front to back, and with the different options that are available here. So this is a simple, very simple shader. All it does is do the object setup and render a color that is constant for the whole object. So this is just to point out that we're rendering the basic pass. And here we have the light mode set as the basic pass. I'll just quickly show inside Unity what we all talked about. So here's the graphics setting window. Right now we are setting set it at no render pipeline. What we simply have to do is to drag our object or set it from the menu here. And this now can render our cube. Our cube is simply a cube that has our shader bound on the material, which is the shader that I showed before with a bit more code since I cut it for showing in a presentation. Whoops, I forgot to. So it's simply the same shader. The render pipeline itself is essentially the same code as we've shown before, containing the pipeline itself that calls the render function on the asset. The render function, as shown before, it's essentially the same code. We do the culling, set up the camera, and do the same rendering code as we showed before. So altogether, this brings us this cube. So this shows us that even with a simple example, I don't see the right line. So even with a very simple example, we can see that we control shaders and all the rendering. So we had a simple forward pass. We could provide different shader passes for different types of pipelines if you want to do deferred or render transparent. We could also provide some shaders to provide some sort of shader LOD. And we can change the input and output of a pass by biting different buffers or render targets. Just as a note, the render passes is actually one of the big features that changed with the release of 2017.1. Some code I'll show a bit later will be modified because we don't need to clear and manage the render targets manually. They're done by the code now. As we mentioned before, the C++ part does the object operation. So they're written targeting more higher performance and using packed arrays and multi-threading. The functionality that from the last example that we'll call the C++ are the culling, draw renderers, and draw shadows will be the next demo. So let's go back to some code. I will explain a bit the code that we're going to see here, and I'll go back to Visual Studio and Unity. So I will be showing mostly the scriptable rendering pipeline code. I won't show the shader code itself. The next parts are using the legacy shaders, so the ones that are already provided with Unity. So in the code, I often show a profiling sample class, which is essentially just this. In a constructor, we are calling begin sample and then executing the common buffer. And when the object is being destroyed, we call end sample. So this is used to have a scope object that does the profiling. So to add the transparent objects, all we need to do here is to have a different sorting, which is the common transparent, which does a back to front sorting, and then we set the queues to the transparent objects. Here we set the shader pass name to forward base, which is the name that you would use in the standard shaders. And the different settings are to enable and disable different options on the shader. And again, we call the function draw renderers. Another example is if you want to do geometry buffer or deferred rendering, you would set an array of render targets. And again, it's essentially the same type of code to do the rest. The shader pass is going to be called deferred in this case, and we're going to be rendering the opaque queue. So for shadows, Unity does cascade shadows, and we also have a screen space shadows. What the screen space shadows does is simply test the depth buffer with the cascades and build a screen space shadow map. So this is the code that renders one of the cascade split. So you would call this once for each of the cascades and sending in parameter the different projection and the parameters that you need for the viewport to render in the correct section of the shadow map. Oh, and this calls the draw shadows function and not the draw renderers. This simply sets the pipeline to only draw on the depth. The screen space shadows, they're essentially the same code as you would do for a post-process, so they're a good example to show. In this case, we are creating a new render target, the temporary render target, and then we are setting it, and then we're clearing it to magenta, which is a default color that the legacy pipeline does. After that, we set the different params on the pipeline, which at this point, there's a bug in the pipeline for shadows, so I could not complete this feature, so it doesn't bind anything. The rest is setting the global textures and then blitting the result. So I will show. So here is again a scene without the render pipeline set. So right now we're not able to render anything. So in graphics, we'll set the forward render pipeline. And now we have the scene rendered with the forward shaders. What we have here is a simple forward pipeline with rendering of only opaques. If we notice here in the scene view, we'll have a couple spheres that are transparent and not rendered at all. Reason for this is we never enable this queue to be rendered. So here we have so I separated the code here just by different passes so I can easily turn them on and off. So by doing this, I now turn on the code for rendering transparents. And here we were only rendering opaque objects. So I will have my function called both for the transparent and the opaque objects. So they're simply calling two different functions. The real part here to actually render the transparency is here. And it's essentially the same code as I shown before. We set the hues to transparent and we sort back to front. So now by saving this, letting it time for compilation, and now we have our transparent objects. Actually, I should probably show here frame debugger. So from the frame debugger here, we see all the paths that we set up. So from the forward pass, we render all the objects that are opaque. Then we render the skybox. And what I just added is these three spheres to be drawn, transparent ones. If we want to do shadows, we would uncomment this. Oh. Which we'll call this code, which simply sets up, where's the function? Render here. Which is the same code as that I showed before. And here the same code Well, here we'll loop over all the different cascades, but the render shadow split is here, which is the same code as we shown before, with code I was working on to set the proper bias on the objects. Currently, the bias is a problem with 5.6, but they are fixing it in 2017.1. So now I should have my shadow pass here. With no objects marked for shadow. Oh, shadow needs the depth prepass. I forgot to uncomment it. I will get back to it later. And you would do the same if you want to do the G buffer. Here I have a simple class that initialize different buffers for the G buffer. And we simply get a temporary render target. And when we get them, we simply return an array that we bind on the pipeline as we shown before. So the rendering of the G buffer is simply an opaque draw like this, and it calls with the deferred shader as we've shown before. I'll just uncomment everything. So here we don't see much, but this is our pre-pass for the depth. And the forward pass here that we showed before, and the different passes. So what could we build with this next? We could build techniques of features that are not yet supported by Unity. New post-processing effects that we don't support yet. We could also research for new techniques, especially techniques that might have required different information from the geometry buffer. We could implement new shading or lighting algorithms. Examples of that are the tile lighting or forward plus. And we could also implement platform-specific pipelines. Could build one for PS4 or for Xbox One or for different phones or different targets on PCs. In summary, we are responsible for doing the calling and the rendering. It includes the per frame and per pass, all the shader uniform variables, management of render targets, and dispatching the compute. All the visible lights and the probes can also be queried from the call results. This is useful for different lighting techniques. We don't do any per object operations, which means that everything is independent from scene complexity. The key takeaways is it's very easy to create new pipelines that suits your need. Different features per platform or different materials per platform. Meaning we could have different materials built specifically for each platforms. You can add and remove features when you need to help with performance. There's no sorcery. All the source code is on GitHub. Good examples will be available. and the interface will be documented. So the IO level view of the rendering pipeline, it removes the complexity, but it still allows more flexibility for Unity. It allows you to modify all the things that are currently in there in the rendering pipeline. Currently, there's no way to work at the object level. You can't modify the culling, and you can't change the rendering of a single object. The only control you have is on the shader itself that you can change. And download the code on GitHub. From that, you can start building your own pipelines and test your own features. But as the new release will come, the code will change, and you need to adapt your code. And thank you.